Hey everyone, what's going on? It's Mr. Anderson, and today I'm here to talk to you guys about section 6.2.3 from our CPM Common Core Algebra ebook. And we're going to investigate this question that is leveraged at the top of your page here. Why can't studies determine cause and effect? Some of you guys know outright from the onset that only an experiment can, a well-designed experiment can allow us to do that. But let's really do the deep dive on why association is not causation. And I just used a couple relatively big words there. So I'm going to start by breaking that down. I've got a couple notes taken here and ready to use for you guys. And so what I hope is that you'll follow along with me and your own notes. And what we're going to do today is we're really going to get to the bottom. I'm sorry, I got to change the color. The bottom of this. Sorry about that. I got to do this now. Oh no. The bottom of this statement. And what does that really mean? And association is not causation. Association, remember, is a fancy word for relationship. And when two variables are associated, or there's an association between two variables, it means they're in relation. It means there's a relationship between those two things. But then it says is not causation. And what that means is it is not necessarily implying that one, and here's the key word, causes the other to happen. Okay, and we think this all the time. We think because two variables are related that one causes the other. And we're going to start to break this down with our first problem today. And before our first problem, I'm sorry. It is with this statement here that says a study found that more hours spent on activities outside of school, the higher their grades tended to be when it comes to students. Does it mean that if you sign up for more activities, your grades are going to go up? Man, wouldn't that be sweet? Right? Students would play every single sport, participate in every single activity, drama, debate, music, choir, all those things, if that meant higher grades. Right? One does not cause the other. There's a relationship. Those two things are related, but there's other lurking variables in there that might cause us to think they're associated. That they're causal. Okay? Another study found the link between how often you brush your teeth and a reduction in heart disease. Does this mean that if you brush your teeth twice a day, your heart's going to be healthier? Man, as somebody who's getting to be an older guy, I'd brush my teeth 10 times a day if it meant like just perfect heart health. But that's not the case, right? And some of you are like chuckling right now that it's preposterous, it's silly, right? But there's a relationship between those two things. Okay, one more. As a consumer, of statistical information, you need to be aware of the difference between the association and the causation. Today's investigation will explore that difference. So here's the one more that I got for you, and then we're going to take this to the next level here. And we are going to use 6-79 from our CPM ebook, and it focuses on some information that was gathered from maybe a fire hose manufacturer, and we're really going to focus in on one of these variables here. I've got a graph for your digestion here in a moment, so we're going to look at that. This is a graph of the residuals, by the way, not a graph of our our bivariate data, right? But check it out. Fire hoses come in different diameters, and that just means the size of the hose varies based on maybe your needs. How far the hose can throw water depends on the diameter of the hose. Obviously, it depends on other things, but one of the main variables, the one that we're after right now, is the diameter of the hose. The Smallville Fire Department collected data about their fire hoses. The residual plot for the data is shown right here. Okay, we've got that residual plot. And part A asked me maybe a little bit of a review idea from a previous lesson. So let's go there first. What does the residual plot tell you about the LSRL, or the least squares regression line model the fire department used? Well, here's what I'm looking at. Okay, I'm looking in my residual plot to make sure that there is no obvious pattern. Okay, now what I see is 1, 2, 3, 4 points below the x-axis. Then I see 1, 2, 3, 4 points above, and then I see 3 down here. And some of you guys are connecting probably like doing it very well, connecting those two kind of are stacked, and that's okay. And what picture this is painting for me is that I've got a very, very curved pattern in my residual plot. And remember, when we've got a curved pattern in our residual plot, a linear model is not going to be an appropriate model for that, right? Because if there's predictability in our residual plot, a linear model is not going to be the best model. There's other kinds of models that we can use, and we'll get there, all right? But what I said was a line may not have been the best way to model this data. The residual plot has a definite U-shaped pattern, right? Obviously, it's like upside down U, but it is a U-shaped pattern. That's present and relevant here, okay? Now, part B says, go ahead and find the worst prediction made with the least squares regression line. How different was the worst prediction from what was actually observed? Explain why in context. So again, I'm going to zoom back in on my residual plot here. And remember, each residual is just an error. Okay, so when I'm looking for the worst prediction, I'm looking for the residual that is farthest away from the x-axis, or no error, right? Something on the x-axis is going to be zero error. So I'm just going to start to do some thinking here. Some of the ones that are really, really far away, and I might have to slide this over because that looks like I'm hiding a dot there. Some of the ones that are really, really far away, like the two that I guess I would consider, that one's really far away. And then this one's really far away. Okay, but which one is farther? Well, let's see here. This residual, what does that look like? Maybe like 22. That's a positive residual of 22. This residual looks like, oh man, that's closer to 25. I'd call that 24, but because it's below the x-axis, I'd call it negative 24. I'm going to call that residual right there the biggest error, or the residual that is farthest away. And that's what, that's what I tried to say here. The worst prediction was for a 3.5-inch fire hose, right? And that 3.5 inches came from that measurement right there. That's the size or the diameter of that fire hose. And it was 24 feet off, right? And specifically, it was 24 feet off in a situation that could be pretty significant, right? It was under. The model expected the water to be thrown 24 feet more than it actually was. And think of how significant that could be. Right? If you're a firefighter and you're standing here, you say, yeah, I can hit that burning building there. And you go to fire up that hose, and all of a sudden, it shorts you by 24 feet. Whoa, that could be catastrophic in terms of loss of life, loss of property, stuff like that. And that's why that really is significant. Okay? Finally, part C says, make a conjecture about what the original scatter plot might have looked like and try to sketch it. Label both axes. Well, ladies and gents, this is a tough thing. I'm going to walk through this with you here. First and foremost, our scatter plots are going to contain only what's called our first quadrant, right? Because we're dealing in like non-negative x and y values here. I can still have my hose diameter here, and then my residuals kind of give me the impression that the units I'm dealing with are feet. So this might be the distance that my fire hose is spraying in feet. Okay. And this would be in inches. Sorry about that. Okay. And then what I'm going to do is I'm just going to throw a line on my screen. Okay. And my line is going to be something like this. Okay. There's my LSRL. And my first 1, 2, 3, 4 residuals are going to be below. Some are going to be a little further below than the others, and you'll see what I'm doing here. All right, this one's going to be like down here. This one's going to be like down there. We get a little bit closer. This one is pretty gosh darn close. And then I'm off, but I'm off on the other side. I'm well above, right? So it's going to be, let's see, I'm going to be off, but I'm going to be like up here, I'm going to be up here, and then I'm coming like back to there, then I'm a little closer, and then down here I've got one, and then I've got one that's like further down there. And what that tells me, and again, this is a quick sketch, what that tells me is this may not be a great linear model. This might be something that's better modeled with a curve. I can't say that for sure. I don't know what this actual data is. Where we're going might inform some of the decisions that we're we're maybe making or talking about right there, but the linear model may not be the best model, okay? Let's keep on keeping on. Let's take a peek at one more problem that might help do some informing for us. In 6-80, we're going to talk about Smallville still. The mayor of Smallville finds the following graph in the town's annual financial report. It says, describe the association, if any, in the scatter plot. Well, remember, there's always 4 things we're looking to talk about when it comes to a description of the relationship, right? Describe the association means describe the relationship. So I always try to talk about form. I always try to talk about the direction. I always talk about the strength, and I always try to talk about the outliers if there's any. So here's what I would maybe start you thinking. I would maybe start you thinking, okay, if I was to draw my LSRL, right, of course we're going to use computers to do this, but if I was going to draw it, it might look something like that. What that tells me is that the direction is positive, right? So there's a word I'm going to be using, all right? And I don't see any obvious curvature, so I'd say this is looking pretty linear, okay? And then if I put my LSRL there, or if I move it around a little bit, I have the ability here using the app that I'm using, I can see that all the data is reasonably close. Now, I'm not sure because I don't have a scale here, but it's looking pretty good. So I'd call this probably strong. And then, we don't have a formal definition for this yet, but I don't really see an outlier. Maybe that's an outlier, maybe. But remember, outliers are relative to each other. And that's maybe pretty close to that point. Or if I was to move this LSRL again, right? Maybe then it's not an outlier, but then maybe this becomes one, right? So there's a lot to unpack there. And ultimately what I said was, sorry about that. There is a positive linear association of moderate strength with no outliers. And ladies and gentlemen, we can call that moderate. You can call it moderately strong. Sometimes people will combine some of those strength descriptors for that. Okay? Finally, in part B, it says the mayor immediately orders the fire department to send new firefighters to each fire so that there is less damage. Why do you think the mayor said this? Do you agree with the mayor's decision? Explain why or why not. Okay, so here we go. This is the root of what we're after today. Is the fact that there's a relationship implying that there's one variable causing the other? Okay, so let's take a peek at this data and maybe do so in a little bit more depth. We've got the number of new firefighters at the fire, and we've got the amount of damage. Because we have a positive linear relationship, that means as one variable goes up, the other variable goes up. So if you're not an informed mayor, you're going to think, well, if I send new firefighters, I'm sorry, not new firefighters, I'm sorry. If I send more firefighters to the fire, then guess what? I'm going to have more damage. I'm going to have to pay for more repair. Okay? But is that really the case? What else could be impacting this? And you can pause the video if you want to think about it for a second, but I'm going to lead you because some of it's pretty obvious. Why would you send more firefighters to a fire? Well, guess what? Maybe the fire is bigger, right? Maybe the fire is bigger, and because the fire is bigger, maybe it's causing more damage, right? And that's what I tried to say in our statement here. Okay, the mayor said this because the more firefighters, the more damage at the fire. All right, and I'm going to try to slide this because I realize my picture's covering some of that. All right, I don't agree with the mayor's decision. The reason there are more firefighters and more damage is probably because those fires are bigger. Okay, and I realize that this is covering that, so let me just kind of read the last sentence. The firefighters are not causing the damage. The size of the fire is doing that. Okay, so again, the firefighters, the number there, are not causing it. It is the fire that is doing that, right? Okay, ladies and gents, I've got a couple of review preview problems for us, and you're going to see those review preview problems right here. Go ahead, give these things a shot, and ask the questions that come up naturally because you are trying the questions, okay? Ladies and gentlemen, thank you for watching. Have a great day.